Okay, let's talk about Chapter 25, the Milky Way Galaxy. Okay, this is our home galaxy. There's the disk of the galaxy you can see there. Let's talk about the architecture, the spiral structure, the mass, the center, what kind of stars are here, and then how the galaxy formed. Okay, so Milky Way is a pretty cool thing. This was, you could try to measure the Milky Way based on the stars here, and this is one of the first measurements, and he tried to estimate where the sun was in the sky. This is another attempt to explain where the star was in the sky. This was a big deal for people to figure out: are we at the center of the galaxy? Are we somewhere else? Well, it turns out that there is a central bulge at the center, and then we also call it a bar here. It's two things. There's a bar and a bulge. So the bar here is this kind of flat area. The bulge is kind of swells up at the center, and then there's these arms that come off the galaxy. We are about halfway out in the Orion Spur. That is where the sun is, about 26,000 light years from the center of the galaxy, and the whole galaxy is about 100,000 light years across. Okay, so I've mentioned this before, but globular clusters, they live outside the galaxy. They are not in the disk. They are out around among the galaxy. Little wonderful little objects. So what do you care about? Your main thing, we're about halfway out from the center, about 26,000 light years away from the center. So in no particular spot, no really nice place as far as we can tell. Okay, so there's a big difference here. Our galaxy is called a barred spiral galaxy. This galaxy spirals out, okay, and from the center. This one has more of a bar shape and then spirals out. Those are the two types of spiral galaxies. There's either spiral or barred spiral. Okay, so those are your two options, so make sure you're aware of those differences there. Look at this beautiful picture. There's the Milky Way galaxy from our perspective. All the gas and dust along the disk. The central bulge is something like that, where it kind of bulges up near the center. Call it a nuclear bulge. This dark matter halo, when we talk about the dark matter halo, and we'll talk about dark matter later, if we go back to this picture, you have to imagine that there's a sphere of dark matter all around it. So when we say a halo, we're not talking about a little, angel halo above the head. We're talking about a basketball surrounding the Earth, surrounding the entire galaxy. So most of the mass of the galaxy is actually in the form of dark matter, and we don't know what that is. So that's kind of a big deal because we're trying to figure that out. So here you go. This is the galaxies here, the galactic centers here. This is what we call the halo. It's a sphere all the way around it. That's where all the dark matter is within that halo. You've got this area of the galaxy is called the disk. The sun is a little bit exaggerated here, about halfway out from the center, and then the bulge is sort of the central thing. Okay, it's cool history here. So the spiral structure, this is the general idea. The sun is about here. The center of the galaxy is there. And you can see this is relative to the sun, the coordinate system. And so we've tried to map out the stars and how far away they are and try to figure out where we are. So there's the Orion Spur where we exist. There's the bar to our galaxy. And then there's the arms that come out from the galaxy. So that's our general idea of what the structure of the galaxy is. Okay, and yep, that's cool pictures. So this is another idea for the simplified model for the formation of spiral arms. As two things orbit around each other, you'll eventually get this spiral shape. So we pretty well understand that. So the mass of the galaxy, this is a really important thing. We tried to measure the mass of the galaxy by counting stars. We figure most of the mass of the galaxy is going to be in the form of stars, and then there should be gas and dust and all that stuff, but we can try to estimate the density of the gas and dust, and count the number of stars. And we can get a really good idea of the number of stars by measuring the brightness of the galaxy, and then extrapolating from there. One of the other things we do was we compare that mass to the speeds of the stars' rotations. So think about this: if you're on a merry-go-round and you're standing at the edge of the merry-go-round, and your friends start rotating you around, okay? As you go faster and faster and faster, you have to really hold on to those bars, because you're going to start going really fast. You're going to want to be flung out of there and fly off to some space, okay? But you don't, because you're holding on to your hands. Same thing in our galaxy. The forces that have to be balanced, okay, right? You have to pull in, but there's a force that wants to fly you off, fling you out of there. So those two forces have to be balanced for you to be happy on your merry-go-round. Same thing. If you've got stars orbiting a galaxy, these stars, as they go around, the force of gravity is the only thing keeping them on this arc. If you go too fast, just like your hands wouldn't be able to hold, you'd fly off. If you go too fast around here, these stars will escape because the gravity isn't strong enough to hold them. So what we did is we were trying to measure the speeds of the stars here and compare that to the mass, the mass of the galaxy, and determine how much gravitational force there is. And what we found is that these stars out here are going way too fast. They should be flying out of the galaxy. We can't figure out what's holding on to them. So we say the simplest explanation is to say, well, maybe there's just a whole lot more mass, a whole lot more gravity, and we just don't have that capability yet to understand what's going on. So let's just call it dark matter. So this is plotting the orbital velocity of a star from the center of the galaxy. So this here would be, there's our galaxy, okay? Sorry, that was a horrible drawing. Let me erase all this. Okay, so if this is our galaxy, like that, the further away you go, you'd expect these stars to be orbiting slower because there's less gravity out there. It turns out that those stars are orbiting really fast, almost as fast as the rest of the stars. They're same constant velocity on this y-axis, no matter how far away you go from the center of the galaxy. So that's a really big deal. So that's our first evidence for gravity, is that there must be a lot more gravity than we can estimate. So that means just by counting the stars, there isn't enough stuff. So we have to require a thing called dark matter. That's the simplest explanation, truthfully, is just to say there must be some extra stuff out there that we just can't see. It used to be that it was just dark stars, brown dwarfs, black holes, things we can't see. It's just regular matter made of protons and neutrons. Nothing crazy, we just can't see it. Well, now we know, because we looked for it, it's definitely not brown dwarfs, Jupiter-like planets, black holes. All that stuff has been ruled out. So now we say, it's got to be some new particle that we don't quite understand. So that's most of the searches right now for dark matter are looking for a new particle that could explain what dark matter is. Okay? At the center of the galaxy is a supermassive black hole called Sagittarius A star, written like this. Sagittarius A star, or Sag A star, is the supermassive black hole at the center of the galaxy. It's like 4 million times the mass of the sun, 4.6 million. That's a big black hole. In any case, every galaxy has one. Every galaxy has a supermassive black hole at the center. We're still trying to find out or learn what the origin of the supermassive black holes are. Did they form first and then the galaxy formed, or did the galaxy form first and then the black hole formed first? So we don't know. These are cool supernova remnants here, the black hole at the center here. Just showing you this is the galactic center, trying to, another supernova remnant here, so these stars are just blowing up all over the place. Okay, and notice that's a radio image. A lot of radio astronomers look at this kind of stuff. Beautiful image of the galactic center there. And here's a close-up, the Sagittarius A star. And the black hole is in this region here. You can't see the black hole, but it's very bright. It's lighting up its area. It's pretty cool. So here's a really cool picture showing the stars and tracing their orbits. So all these stars are orbiting something at the center of this black hole, or this region. We can't see it, and so that's the best evidence for a black hole is right there. Okay, you'll see Andrea here in a lot of documentaries on PBS or things like that. She does a really good job. All these science stories. Okay, and yeah, okay, so there's two differentials or ways to differentiate where stars are. There's stars that orbit in the disk, and then there's stars that orbit in the halo all which away, and they're different. So there's a beautiful image of Andromeda right here. Two types of stars, population 1, population 2 stars, and they differ not only in their locations in the galaxy, but also their age, their composition, or whatever. Population 1 stars are in the disk, follow circular orbits. Population 2 stars are just all over the place. And let's see, yes, there's some, anyway, our Lyrae variable stars, there's stars here. Globular clusters are outside in the halo, the population 2 stars. So you can think of population 1 stars as still forming to today, and population 2 stars as being very old, that are 11 to 13 billion years old or so. Okay, blah. So how did the formation of the galaxy form? The idea is that gas falls down, creates stars, continues to fall down, creates more stars, and then you end up with the galaxy here. So you have some globular clusters here that formed out of the initial collapse, and then the rest of the centermost part, where most of the matter was, continues to form stars to today. This model is the monolithic collapse model. The multiple merger model is the more kind of accepted model of today, which says that smaller galaxies came together and ended up forming bigger galaxies over time. So here's a cool image of some results of different galactic mergers as they joined the Milky Way. This is really cool. The globular clusters, they're these very dense star clusters that are very old, orbiting around the edges of the galaxy in the halo. Very, very cool. Andromeda and the Milky Way right now will collide. The two galaxies will merge in about 3 billion years, which will be pretty cool. And this is, you can imagine what the night sky might look like while that happens and we start to merge. Of course, it's important to realize that space is super big and super empty, so even when we collide with the Andromeda galaxy, the odds that we'll actually hit anything are basically zero. So we'll just interact with Andromeda and merge, but there won't be any catastrophic collisions or anything. Okay, so in summary, the galaxy, there's a thin disk. It could be barred or unbarred. Ours is a barred spiral galaxy. There's a halo where there's dark matter, population 2 stars, globular clusters. We're about halfway out from the Milky Way's center, about 26,000 light years from the center. We have a spiral structure that is barred. The galaxy has more mass than we can see, and most of it, 95% in fact, of the mass of the galaxy cannot be determined. We cannot figure out what it is, so we call that dark matter. It's dark because it doesn't emit radiation like we normally think of, microwaves, all that kind of stuff. The center of the galaxy, there's a supermassive black hole. There's two populations, old stars and new stars, and we think the galaxy began forming basically at the beginning of the universe. We've got the halo and the globular clusters formed first. The galaxy was still spherical. They're still forming today in the collapse here. And then, the galaxy is continuing to eat other objects, small galaxies, globular clusters, and so on. And in 3 to 4 billion years, we will merge with the Andromeda Galaxy and form the world's greatest band. Okay, that's it. See you guys later.